Okay, so we're going to start off with just thinking about what are the main controls on Arizona climate. And I like to do this as sort of a first step, because I think it's hard for us to understand how climate has varied historically across Arizona and how it may change into the future without having a little bit of context for the uniqueness of Arizona's climate. We have really unique topoclimate and seasonality and precipitation. We have monsoon versus winter storms. We're having this wonderful monsoon season right now, and it's been broken up by a very dry spring and actually quite a dry winter. And then having that failed monsoon last year has given us just a lot of moving parts and pieces that's created really complex drought situations here. So understanding the difference between winter versus summer precipitation. And then this idea of elevation. We have amazing elevation gradients across the state, which then drive really sharp gradients in precipitation. As you drive around the state, you can see the conifer forests up at the upper elevations, and you'll be driving through desert scrub. And so that is a representation of climatic diversity just over very short distances. We also have the El Nino Southern Oscillation, which operates on Arizona climate primarily in the winter and can give us longer term cycles of drought. So it can give us winters when we have La Nina winters, typically drier than average conditions. El Nino winters can give us wetter than average conditions. We don't always have an El Nino or La Nina every winter. So we can have neutral winters in between, which can be kind of a toss-up on what they actually give us as far as precipitation. And then on top of this, so just those two things working together, topoclimate, seasonality, El Nino Southern Oscillation is already giving us lots of variability, both over space and time. Now we have a changing climate on top of this. And so increasing temperatures, and we're not super sure how it's actually changing the variability of precipitation. It may be slightly, but we already have a very variable hydroclimate. We'll talk a little bit about that. But warming temperatures just by themselves increase aridity, drive more evapotranspiration, and we're already seeing the impacts of that across the Southwest. Okay, so I start off with this map of topoclimate, just to give you a sense of the climatic diversity that's just arising from topography. So this is a map of long-term average annual temperatures across the state, and it's developed using station data, so weather stations, airports, national parks, and sometimes in people's backyards. And we take those data and we statistically interpolate them against an elevation grid. So those little squares you can see on this is going to be an elevation grid. And so then we can model what we think temperature is going to be at different elevations. And it works really, really well for temperature, because as we go up in elevation, on average, it gets cooler. And we know that the vegetation tells us that story. We also see these little gray lines here. Those are our major watersheds here across Arizona. And you can see that they run along those high elevation areas, and then they move down into the lower elevations. So these areas have higher elevations with cooler weather conditions, where we have surplus water that'll run off and move down into the lower deserts. So just on temperature alone, lots of climatic diversity. The temperature ranges we see here in Arizona, if you went up to a flatter area, you'd have to go up into Canada, a flat part of Canada, to see the same amount of higher elevation temperatures that we see here in Arizona. And our lower elevations are some of the warmest places in the whole country. So just squished in our one state, given elevation, we have the same diversity you'd see over tens of degrees of latitude out east in the sort of flatter country. So when we move to precipitation, it looks similar. We have that same elevation gradient emerging across the state, but it's a little bit different. You may notice some areas that are actually higher elevation but are drier, and some lower elevation areas that are wetter. And so if you look at the northeast corner of the state, you might notice that that was actually, if we look back at the temperature, is a cool area. It's a high cool desert, though. It's a desert. And this area up here is actually created because of the Mogollon Rim serves as a rain shadow. So as storms try to cross and move across the Mogollon Rim in the wintertime, they're kind of pushed up. We have the precipitation occurring, and that rains out, and then it descends and dries as it moves into the Four Corners region. So that's sort of an indication of a rain shadow area. And if we go look at the southeast part of the state, you may notice that those valleys in between what we call our sky islands down here are a little bit wetter, and that's the monsoon season. So when we get storms forming on the mountains there, they're able to move out in the valleys and give those lower elevation valley locations more precip than you'd see in other parts of the state. say like the northwest corner of the state. So just in these, temperature and precipitation alone, lots of variability emerging around elevation gradients. So we can see this show up. This series of plots here are very similar to what we just talked about here. The upper left is a much finer scale elevation map. The lower left is the same precipitation map we just looked at, just scaled a little bit different. And then we put up this Arizona biome. So just another way of organizing major ecosystems across the state. And what I'd like to kind of draw out of this is the amazing list of biomes that occur in one state. This doesn't happen in every state in the US, especially if you go back east where it's a bit flatter. You don't have that ecological diversity that's driven by this variation in topography. But also this meeting of these deserts as well across Arizona. So that light yellow in the upper left corner is Mojave Desert Scrub. So that's the Mojave Desert. The lower, the southeast corner of the state and the lower right-hand corner of the map there is Chihuahuan Desert Scrub. You see that kind of light, kind of tannish color there. And then in between is the Sonoran Desert. And so those three deserts meet in Arizona. And one of their biggest differences is the Mojave Desert is primarily a winter precipitation desert. So it's connected to the larger Mojave Desert and the Mediterranean climate of California. The Chihuahuan Desert reaches down into New Mexico and into Chihuahua, Mexico, more summer dominated. And then the Sonoran Desert is where they meet together, and they have 2 seasons of precipitation. So those 2 seasons overlapping give us a lot of ecological diversity because of that hydrologic and climatological diversity in the seasonality of precipitation. So this is trying to illustrate seasonality just a little bit more. So what I did is I took, this is from a website, the Westwide Drought Tracker. It's got some great tools on it, but I can look at all of Arizona cookie cut out, and I look at the data going back in time, monthly data that goes back to 1895. And again, it's that same kind of gridded data we were looking at before. And it's going to come up with one number for each month in that whole period of record for Arizona. So it's taking the wettest and driest areas, and it's just creating an index of precip for Arizona. And then what we can do is we can organize it by month as far as looking at its distribution. So I want to draw your attention to is that black line that moves across this plot from left to right is giving us an indication of the median, similar to what we would think about statistically as the average. We can call it the average for intensive purposes now, but that is the indication of what is the average monthly climate as we go through the year. It starts on October, November, December, we go all the way to September. So that's the water year too. That's another way we look at climate down here in Arizona. We can do the calendar year. The water year is a little more respectful of the seasonality of precip because it's right after the monsoon season into our winter season and then spring and summer. But what I want to illustrate with this is this kind of pulse, the breathing of the hydroclimate here, which is from October, November, December, we kind of move up into, I'm using my air quotes, our wet season here, so that you can see that black line kind of moves up a little bit, falls off quickly in the spring. We have a very reliable spring, also known as an arid foresummer, because spring is a bit generous sometimes. It's a very dry and hot season. And then that really rapid shift from very dry, driest month of the year is June, into July, which becomes one of our wettest months, which is that rapid transition into the monsoon season, typically peaking in August on average, and then we fall off quickly in September, and then we start the water year over again. The blue areas give us an indication of historically how much range of variability has there been in these seasons. And so you can see in that wintertime season from December through March, there's large band around that. And that gives us an indication we've got very dry years and very wet years in there. Spring, it shrinks. It's pretty reliably dry. We don't have any in the historical records, very wet Mays or very wet Junes. They can occur, but they typically aren't anything like we see in the winter or the summer. And then as you get in the summer, you can see that really open up again and see a lot of that variability. So it's these 2 seasons become really important in Arizona. We pay attention to the winter and the summer differently. We look to them to give us different things as far as water, and how they may change in the future is really one of the things that we're really interested in looking at. All right, so the seasonal distribution of precipitation is kind of the point I'm driving at here. We're going to look a little more closely across the state here, and these are what we call climate divisions. They're just multi-county areas, and And Yavapai County, lucky enough, has its own climate division. And you're I think the only, well, and sorry, Gila County does too. So Gila and Yavapai County have their own climate divisions. Every other climate division is a grouping of counties. So I'm down here in Pima County. It's got Santa Cruz, Cochise, Graham, and Greenlee all squished together. But we take in those areas, all that station data. These are little climographs, and their bars represent the long-term average monthly precipitation for January through December. So just like we looked at before, but now calendar year, the length of the bar is proportional to the amount of precipitation on average that month gets. So what it's showing you again is that same kind of at the winter, January, February, March, the bars stand a little taller. They drop off pretty reliably across the state, across the spring, April, May, and June, stand back up again in July, and then we move through the year again. And if you look across the state, there are some differences, right? So Southeast Arizona, those summer bars are much taller. We're much closer to the monsoon activity in Mexico. And as you go further north, you're a little bit further away from it. So we get more reliably get that, that summer precipitation. But as you go further north, you are closer to the winter storm track that tracks across the west in the wintertime. And so those winter bars stand up a little bit more, and at higher elevation, that helps as well. We don't get quite as much snow down here in our Sky Islands as you do in Prescott or even in Flagstaff. So there's just a little bit of difference, just a couple 100 miles apart across our pretty small state. Okay, and then finally, just mechanistically, that other form of variability that really visits us in the wintertime, makes an impact in the wintertime, and leads to variability over longer periods of time, is related to the El Nino Southern Oscillation. The El Nino Southern Oscillation is a periodic shift in sea surface temperatures across the Pacific Ocean along the equator from South America all the way into the West Pacific. And so that area is baking under the sun, and wind patterns above it, below the sea surface temperature pattern in different arrangements, basically. And so during La Nina winters, which is what we had last winter, we end up having much, much colder water than normal off the South American coast. And it seems far away, but what it actually does is it can impact the winter jet stream way upstream and send wave patterns across the Pacific Ocean towards us, and then basically park the storm track away from Arizona and give us drier than average conditions during the La Nina winter. When El Nino events occur, we have warm water across the entire Pacific, all the way to the South American coast, extending back past the international date line. That tends to enhance the storm track and pull it south, and it can park it over us. And so Southern California through Arizona, New Mexico, and all the way into across the Gulf of Mexico into Florida can see wet winters in those El Nino events. So we saw a La Nina event last winter. It was pretty dry. We had a couple of pretty good snow events. I think we got lucky. La Nina events typically are quite dry. We're now looking at a weak La Nina event reemerging. So we might be looking at yet another wet winter, even with this really wet conditions during the monsoon, may slip back into drought this upcoming winter. Okay, so let's take a look at some of the longer term patterns. And so this is looking backwards before we look forwards. And again, I think this is part of that context. So thinking about seasonality, thinking about El Nino Southern Oscillation and these longer term variations. This is an extraction of some data from tree ring reconstructions for wintertime precipitation for Yavapai County or Climate Division 3. This is done by the tree ring lab down here at University of Arizona. And they statistically reconstruct by coring trees, measuring the ring widths back hundreds of years. They can reconstruct that in piece reconstructions together. And then they look at the instrumental record and they statistically look at the correlation between the ring width and how much rainfall actually fell at a rain gauge. And then you can look backwards. And so this plot here is going to go back to 1000 AD, and it's going to end at about 1988. This reconstruction ended. And it's going to give us an indication at 100 is the average, long-term average precipitation for the November through April period. So that's the winter period. These trees are sensitive to winter precipitation. So if you're at 100, you're at the average, and it's percent of average. So 150 is 1.5 times the average, 200 is 2 times the average, 50 is half of the average. So you can just see it, we kind of bob around 100, swing wildly above it, below it, and then You might even notice on some longer time periods, we've got groups of years that are above 100 and groups of years that are below 100. And those are what we call decadal variability in this precip record. And these can be extended wet periods or droughts. But you may notice that there's some pretty extensive drought periods here in this reconstruction record, which gives us some understanding that droughts are not new for the Southwest. They're definitely part of our natural climate variability. And we've known that for quite a while. And tree ring reconstructions and paleoclimatologists have really helped us get our head around that. And it's been helpful as we have our water discussions now. The Colorado River Compact was actually signed, and the river was carved up during a wet period. So we didn't have that climatological context when we were doing a lot of our water planning. We have it now, and we understand that we do have deep droughts in our historical past. So if we zoom in now, we're gonna go right into the instrumental record. An instrumental record meaning that this is the period of time when we actually had rain gauges making official measurements, and they're pretty sparse about 1900. They really improve about 1930, and they get better through time. But we can make this estimate anyways back to 1900. Same thing, looking at all of Arizona. So the average precipitation for the wettest and driest locations across all of Arizona. Each of these bars then is the calendar year average precipitation for Arizona starting in 1900, and it ends at 2020. So it goes right through December of 2020. So it's just about 8 months old on this record here. And it looks similar to what we saw in that previous paleoclimate reconstruction. You kind of notice the moving up and down, the grouping of years that are above average, grouping of years that are below average. We see that the 1900s into the 1920s, more of those years were above average than below. Then as we get from about 1940 through the 50s into the early 60s, more of those years are below average. So there's a dry period, it's a historic drought period in Arizona. Then we move into the very wet 80s. So from about the mid 70s through the 80s and into the early 90s, more of those years were above average, quite wet in the 80s through right about 1990. Many of those years are very wet, much above average with very few dry years. And then since about 1995, maybe 1999, we've really started to see that shift again back to more dry years than wet years. Again, decadal variability. We know that decadal variability is part of the El Nino Southern Oscillation. We have groups of years that have more El Nino winters, groups of years and those are wetter periods, groups of years that have more La Nina winters, those are the drier periods. So the 50s, more La Nina. And we've seen since about 1999, really kind of falling back into that more La Nina-ish period. Couple of wet years here and there, but again, still sort of struggling to maintain average in most of these years. 2020 really stands out as being very dry. You can look across here at the very short bar at the very right-hand side of the screen is 2020. And you have to go back to about 1956 to see something as similar and small. The interesting thing, I've been looking at the data, is that between 1954, 55, and 56, very dry winters, very wet summer right in the middle of it. 1955 was, for Tucson anyways, was the second wettest monsoon on record in between these very dry winters. And so it feels pretty reminiscent, even in the pattern that we're seeing, to what we saw in the mid 50s. Doesn't really give us an indication of what we'll see next winter or even next summer, but it was interesting to see some of these kind of twins in the historical record kind of combing back through them. Okay, so we can draw this out. This is converting that same plot of the green bars into a drought index, and it just enhances the wet years and the dry years. Blue bars standing up are wet years, and these are scaled to standard deviation units, if you remember statistics. So the very tall bars are very rare. As they get closer to zero, they're more normal, quote unquote, or near the average. And so 2020 really stands out, but precip wise was actually drier in 1956. So we didn't quite beat it as far as just raw precipitation totals in this particular drought index. But it is different now than it was in 1956. It's quite a bit warmer. And this is the climate change aspect of this story, is that it's getting warmer. This is not related to decadal variability. This is related to global climate change on a global scale and its expression down here in the Southwest. And you can see this at local records as well, is that, a little bit up and down, dry periods in the 50s drought tended to be a little bit warmer because when it's dry, typically have fewer clouds, warmer temperatures. But since then, we've kind of broken away from that. And even wet years are now warmer than they were in the past, and dry years are even warmer than they were in the past. So 2020 now stands out as the warmest year on record in this historical record. And if we bring those two things together, knowing that warm conditions also enhance drought intensity, under warmer conditions, we end up having more evapotranspirative demand. That's that atmospheric thirst. How thirsty is the atmosphere to pull water out of plants, out of water bodies, out of the soil? Warmer conditions create more intense drought conditions as well. So you can see now 1956 still stands out here, but our more recent droughts that weren't quite as dry as 1956 are now more intense drought-wise, and 2020 just sinks everybody as far as its drought intensity, because missing that monsoon precipitation as well as missing the clouds that would have came with that really caused the temperatures to rise and created that feedback of high temperatures. We can see this on a map here too. So this is December 2020 in the upper left. This is a 12-month backward looking map here. So it's the whole calendar year of 2020. And reds are never really good on climate maps. Whenever you see red, it's usually something bad. And here it's indicating very dry conditions. And that darkest red there, you can see splotches of it across Arizona. So those would be record dry conditions in the historical record. It's a 120-year record across the Southwest. And then on the right side there is giving us an indication of the temperatures. That dark red is the record warmest. So record dry, record warm, put those together, you get the most intense drought conditions in this 12-month period that we've seen in the last 120 years colliding together. All right, so warming temperatures can shift the average soil water balance. So this is the creeping crowd aspect of climate change and drought down here, is that increasing temps lead to increasing potential evapotranspiration, which is really what we're talking about when we have that, is increasing aridity. So drought becomes an improper term at that point. Drought is supposed to describe a condition that doesn't last forever. It should be an event that has a beginning and an end. When you're talking about a shifting baseline as it's getting warmer, you're actually indicating that the place is changing to a more arid state. So as it gets warmer, more evaporative demand, then you have more evaporative demand, which increases aridity. So the same amount of precipitation is leaving more quickly, which gives us an indication of aridity. So this is an on average over time thing. So very wet summers like this are hugely beneficial, but what we need this level of precipitation to counteract the increasing temperatures to maintain the same level of aridity that we had in the past. And so this also has to do with the timing of precipitation and the kind of precipitation we get, snow versus rain, when and how often and how much. So again, this monsoon's been fantastic, but we've gotten an annual amount of precipitation in a couple of weeks. It's not the most effective or efficient way to keep an ecosystem going. It just puts a lot of water everywhere and it just runs off every place and the soil can't hold it. So we're really looking to not have major shifts in the ecosystems. We need to keep the precip increasing over time, and the projections aren't real clear that that's going to happen. Okay, so just to give you an indication, this is to bring us up to present. I was looking at some data from Prescott, one of the cooperative observer stations in Prescott, and this is the water year. So this is back October 2020, the daily precipitation accumulation across this plot here. So those little blue bars are what happened on every day up in the water year, and this is updated through 2 days ago. There's little blue asterisks at the bottom that are hard to see. Those were snow days. And that blue line that kind of grows is the cumulative total precip. The brown area with the black line on top of it is the normal accumulation. So if it was a wet year, you would have been at that line or above it, and it would have looked slightly green. And you can see here that the whole winter, this was a dry winter, didn't quite keep pace with the amount of precipitation that we expected last winter. It was a La Nina winter, and we ended up having dry conditions. But this monsoon has been quite spectacular, and you can see here that you've almost made up the deficit in water year precipitation and even crossed over. There's a little green area where the total precipitation for the water year just crossed over in the last couple of weeks. So there's still a chance that Prescott could have average water year precipitation even after having that very dry winter by getting all of it, just about all of it in the summertime. Weird. This is not a usual situation. And again, evenness of precipitation is usually what we're looking for. We like it to be closer to average because the whole ecosystem and all of our resources are kind of organized around that. But we know that we've got a highly variable climate and we expect to see these things happen every once in a while. Okay, so we're going to move right into the sort of the climate change aspect of this talk and talk a little bit about climate change. And so it all starts here and it kind of ends here too, because this is the basics. You know, the IPCC report that's out recently is about 4,000 pages long and it's got a lot of stuff in it, but it all comes back to this very basic thing of what is the greenhouse effect? How do we know that changes in the greenhouse gases in the atmosphere are actually causing changes that we're seeing across the planet? And it has to do with the fact that we know this. You can do an experiment at home with some household products to actually demonstrate this trapping of energy in the atmosphere related to having high energy solar radiation from the sun go through our atmosphere, basically unimpeded, unless it hits a cloud and is reflected back out to space. But if it makes it to the ground absorbs it. And as soon as that high energy radiation from the sun is absorbed, it cools way down and then re-radiates that energy at a much, much longer wavelength and a cooler temperature, still hot. But then that long wave radiation, as it tries to go back out to space, starts to excite these greenhouse gases. And these greenhouse gases didn't care about the sun's energy coming in at short wavelengths, but it does care about it going back out as long wavelengths. And so this little cute carbon dioxide molecule here is it's interacting with infrared radiation or this long wave radiation. Just the shape of the molecule, and this is with some of these other greenhouse gases, it tends to get excited by that and it vibrates a little bit more. And as it does that, it releases energy. And if it is excited and releases energy, it releases it both back up, but also back down. And if you have any extra energy coming back down, that's slowed up energy and energy that turns into sensible heat and trapped energy in the whole system. And so the greenhouse effect is very important for us. If we didn't have the greenhouse effect, we'd be an ice planet and it wouldn't support life. So it's actually an important part of the system, but it was kind of finely tuned and we evolved with this fine tuning. And so the changes that we've seen over the last 1,000 years have been pretty dramatic just in the last 150. So that top plot is temperature change from 1,000 to, this was an older figure from 2000 IPCC report. The CO2 concentrations rapidly rising and then in lockstep with the carbon emissions. So just sort of putting all these things together, the Industrial Revolution, really important for the advance of society, but has had this unintended consequence of releasing greenhouse gases into the atmosphere, which we're now sort of seeing the effects of. And we can look at this a little more closely. This is from a more recent report from 2017, the National Climate Change Assessment. Carbon dioxide up at the upper plot here. This is actually going back 800,000 years, and we can do that by coring into ice. We extract little bubbles of actual atmosphere that were stored in layers of snow that happened every year over 8,000 years. And you can see here that it goes up and down this carbon dioxide concentration in parts per million, but has really dramatically risen in the last 150 years. And we've crossed over 400 parts per million recently. This middle plot here is methane. Same sort of thing, dramatic rise more recently. And then nitrous oxide down here is at the bottom. Concentrations have varied quite a bit, but then large changes just in the last 150 years. So we put all these things together and we know CO2 is going up, we know temperature is going up, but that's not the whole story. That's just correlation. It doesn't necessarily have causation associated with it. So how do we actually know that one thing is causing the other? And this is where climate science actually performs experiments, right? And so this is something called attribution. We do attribution studies or attribution experiments. And the trick with climate science is that we're not able to do benchtop experiments the same way a physicist or a chemist would do to actually have a control and a manipulation and be able to test a hypothesis that way, or like a field trial with an ecological experiment where you had a control and you manipulated something to see if that effect is. We actually have to do this through modeling. And so we build computer models with all the physics and thermodynamics represented through mathematical models, and then try to as best represent all of those processes to then change some of these variables to see if we can recreate what has happened in the past. So this is from an older experiment. It's been repeated and repeated and repeated. But it's, if we look at the observed temperature record for the whole globe, which is that black line, you can see it kind of bobbing around since prior to 1900, and then it rises quickly in the end of the record. We run two experiments, or there's two experiments run in this particular paper. Natural variability, the model has volcanic eruptions and solar variability related to the 11-year solar cycle, which does indeed have some control on climate. That's the blue experiment. And then the red experiment is going to be volcanoes, solar, greenhouse gas forcings, and sulfates. So both, both cooling effects and warming effects together. And as you see here, what experiment lines up best with what was observed is having the anthropogenic, or those human-caused changes in the model, is necessary to more closely follow the observed record, especially since the 1970s. So they kind of really diverge. And so that blue line suggests if we didn't have greenhouse gas forcing, we would have had kind of more bobbing around the long-term mean rather than this trend upward. And these experiments can go further, and we can parse out the attribution into different pieces and parts. And so this is from a 2018 National Climate Assessment report. And I'll share these slides with you if you want to really dig into these links and kind of dive a little bit deeper here. I know I'm going pretty fast, but natural influences at the upper here will be bobbing around zero. So it does have a net warming or a net cooling effect. If it's above zero, it's a net warming. If it's below zero, it's net cooling. So you can see here, volcanoes, solar, and orbital forcing, very small changes over the last 100 years, with large changes in the observed record with the black line moving up there. And then all human influences in the middle panel there, you can see the greenhouse gas forcing is actually above, that purple line is above the observed black line there, which means that there have been some compensating cooling effects from other changes. So changes in ozone, changes in land cover, and changes in aerosols. So aerosols meaning just sort of dirty air. Dirty air can actually create less incoming solar radiation and cool the planet slightly. It's the same thing as like a volcano. Volcanic eruptions temporarily cool the planet, and but once that ash falls out, the solar radiation is allowed to come back in. So down here, this attribution exercise, you put all these things together, it gives you a pretty close fit to what we've observed, gives us some confidence that the models are getting the big parts and pieces of the climate system pretty well. Okay, so we kind of finally moved through some climate projections looking forward here. We start off though with just some best practices and some ideas around what are climate projections for and how do we best use them. So in my job, working in Arizona and working in extension and working with water managers, resource managers, farmers and ranchers, communities on planning around climate, a lot of questions are like, well, what's it going to be like in the next 10 years? Unfortunately, we don't know. That is where the modeling is its most uncertain. So in the next 10 years, the things that cause climate to vary the most are going to be things like El Nino Southern Oscillation and other surprises that we don't actually have great scientific certainty about, and just lots of internal variability. But as you get further out in the record and we push out to later part of the century, the scientific uncertainty goes down, but the scenario uncertainty gets bigger. And what we mean by that is scenario uncertainty is, what are we going to do with greenhouse gases and what other technological changes are we going to make? So as we get away from the short term, we get into the long term, changes in final greenhouse gas concentrations later in the century become the most important determinant of where these projections go. And hopefully that'll make a little more sense in a couple of slides. And this possible futures in these scenarios, you may hear about this in the news a little bit, but what ends up happening in the IPCC report, Intergovernmental Panel on Climate Change, which had a lot of reporting, very recent assessment report 1 came out, Working Group 1, and they have to, in their modeling efforts, think about what greenhouse gas concentrations might look like every year out into the future. And you can envision that there's lots of possibilities, right? There's possibilities where we use more than we're using now. There's possibilities where there's some major technological shift that we're not sure about that will happen in 10 years and greenhouse gases go off or reduce really quickly, or we invent some negative emissions technology in 20 years that brings emissions down really quickly. Geopolitics, technology, political science all come into play with these pathways. So the International Energy Agency is involved with this, and so teams of scientists across the whole planet. And you get these different scenarios. So there are these really strange names too, but the numbers here, like 8.5, have physical meaning. They actually mean the amount of watts per meter squared of additional energy that's trapped in the planet at end of century. And so 8.5 is 8.5 extra watts per meter squared that's trapped in the atmosphere, trapped in at the surface that we didn't have before. And that a watt per meter squared is like one of those old Christmas light bulbs, that the incandescent ones, you know, you could actually kind of feel the warmth. 8 of those for every square meter for across the whole planet of additional warming, right? So that's a lot. So that's a big shift. It's also probably highly unlikely at this point, given our understanding of how systems work and just how difficult it is to get fossil fuels out of the ground. This would take a great effort on our part across humanity to really double down on fossil fuels, and we're bending the curve away from that right now. So that's highly unlikely at this point. So and it says business as usual. So unlikely is even. This 7 point, which is very high as well, probably unlikely. This we'd have to go backwards. Hopefully we can continue to go forward, but that would require unraveling some of our progress. So we get down here, and this is where you've heard about like 1.5 degree C of warming versus 2.5 versus 3. So we're all the way down here now, and we really want to try to get to 1.5, which is, as you can see here, very it's going to take a lot of work, right? Because that's actually dropping emissions off very quickly and going negative by mid-century. And this 2.5, which would be pretty dramatic as well, is kind of probably current here. And so you can see their historical and pledged policies. And this is from last year, I believe. This little, if you're really into this stuff, and this stuff is such a rabbit hole, and it's really interesting, but it's very complex, and I do not have my head around all of it. But there's a great little, I put this link here, a great explainer if you really want to dive into these things, because they're really quite fascinating on their own right, and it gets into the technology and policy of everything. Point of all this is I'm going to show you some projections, and I'm going to show you some projections that range from about this kind of blue line of 4.5 and 8.5. So it's very wide differences. One is almost probably impossible, the higher emission scenario, and the one at the lower end is probably more likely. Okay. All right, I'm going to pull some data from this climatetoolbox.org, which is really nice, but this has got older projection data. There's a brand new set of projections just out this year that'll take a couple years for it to filter back out into all of our tools. But this is still, I think, fairly straightforward and interpretable. So I dropped a pin on Prescott, and we're looking at summer temp. I'm sorry, this should say Prescott at the top. I apologize, this is Tucson for a different presentation, but these are Prescott selections here that show up here. And so it's the lower emission scenario, 4.5, is at the top, and the higher emission scenario, which is most likely unlikely at this point, is at the bottom. And so it gives you an indication here of the historic past, and then we push out to end of century. And so in the lower emission scenario, you know, we're still looking at about 6 degrees warming for Prescott. So your average highs in the summer of about 85 turn into about 91 degrees. And that's noticeable. On the highest end, it's about a 7-degree jump in those hottest temperatures. So if you're, you know, experiencing 95 by end of century, it could be 102 degrees at this 4.5 emission scenario. At the 8.5, we really push it. You get into some pretty crazy numbers here. So I think, you know, just thinking of Prescott at 107 degrees is pretty miserable, and I don't want to think about that. Which is, this gives me some, you know, added energy to say we should really turn this thing around. We can look at this as far as annual average temperature. Again, this is Prescott, and you can see here that those two emission scenarios are kind of diverging, just at what you expect here. lower emission scenario doesn't go quite as high or quite as fast, and the higher emission scenario does. Pretty straightforward. More greenhouse gases, more heat in the atmosphere, temperature trend goes up. Gets interesting. We look at annual precip for Prescott here. You see this black line is looking backwards, historical variability. The gray area around is the historical variability, and this would be the long-term mean here. As we go forward, you can see here that the blue and the red lines, they kind of just hug the same level. They don't get dramatically higher or lower, and they sort of spread out. There's more variability. That's kind of what the climate projections say. They don't suggest we're going to get any drier or wetter. They expect that we're going to have the same kind of variability, maybe more variability. So maybe more swinging between wet and dry years, which we've done in the past, but maybe it's a little bit more erratic. Again, we're not totally sure going forward. Break them up by season here too, kind of looks the same. The winter, same, lots of variability from year to year, no general change out through end of century. Same in the summer. The summer is a little interesting. It gets a little bit wetter towards the end of the century. It's hard to believe the models actually have that well represented, and more variability in the summertime as well. I'm not sure I totally buy that, but at least in the short term over the next 50 years, doesn't seem to be major reorganization and shift in the amount of precipitation. It's just going to be warmer. And again, that's information for us because we know that evapotranspiration increases, we get more arid. So even under the same precipitation variability, the place gets drier. And we're seeing that already right now. And then finally here, just to pull out a plot here, this is actually the new slate of climate projections out this year. And so the CMIP 6 is an indication of the version. And so we're just looking at CMIP 5. We're looking at CMIP 6 projections right here. And it's January, February, March, precipitation on the left, July, August, September, precipitation on the right. Greens are increase in precipitation, 0 is no change, reds are drying. And so it's interesting to see this. This is a little bit of a shift here from last time, is that Arizona is at this break point in the wintertime, seems to get wetter in north of here, which is didn't really show up much in the last set of projections. So this is kind of new, and it's drier to the south. This is the sort of expansion of the subtropical highs in the wintertime. So the bottom plots give us an indication if there's increasing variability. So it's kind of what we were talking about before. Could slightly be wetter, looks like no change across to Arizona, but increasing variability from year to year. So that increasing variability is probably something to contend with. This on the right here is interesting to see. This is a kind of an enhanced monsoon signal, which is popped up in this new set of projections. And the bottom here is showing us a little bit of increase in variability across Southwest Arizona, but a lot more study needs to go into looking at these projections to try to understand them a little bit more. And then the temperature it's pretty straightforward. It's just going to get warmer. And again, this is an emission scenario, which is right in the middle. This is actually the 7.0. So this would be the high end emission scenario. So again, quite a bit of warming, more warming to the north of us in the wintertime, and the same in the summertime. So Arizona still gets warmer, but our friends to the north and the west even get more heat than we've even seen, not in scale, but seeing more change than we have seen even here in the Southwest. Okay, I'm going to skip that. I'm just going to kind of round it out here and talk about the closing points. Okay, so complex hydroclimatic variability at weather timescales dominates all of Arizona, leads to high levels of interannual variability. So that punchline of variability is us. That's what we do. We do it well, and we've seen it in the past. We should expect it in the future. So they have higher variability in the future, though. So having and maybe enhancing a little bit more. And those precip projections, we still have a lot of work to do there. We may never really get a good solid answer on what those changes look like in the future. But these temperatures are expected to warm dramatically in this century under this high emission scenario. Every bit we can do to bring that emission scenario down is helpful for everybody. It's going to be helpful for us. And so we're really kind of gunning for those lower emission scenarios to try to limit the amount of warming that we see. But we have to adapt at the same time as we mitigate. So these higher temperatures are going to decrease snowpack, and they increase the levels of evapotranspiration. So it's a shift towards increasing aridity. It's just how much aridity are we going to see in the future? Can precip keep up? Boy, oh boy, a foot of rain in 6 weeks sure helps, but be better if we got that spread out over a couple of seasons and a couple of years. And so our variability doesn't tend to give us a lot of favor in keeping up. So we're going to really have to keep our eye on increasing aridity as we go forward. Okay, that's all I have. Thanks for your attention, and I'm happy to field some questions if anybody has any.
One I saw in the chat earlier, which may have been covered by those images, was what changes can we anticipate with warming ocean temperatures?
Yeah, it's a good question. Warming ocean temperatures tend to release more water vapor into the atmosphere and enhance precipitation. So we already have seen real subtle changes, 7 to 10% increase in water vapor in the atmosphere. That leads to heavier rainfall events across different parts of the world. And you know, some of those water vapor molecules that fell out of our monsoon rainstorms this summer are enhanced and added because of those warming temperatures.
I have a question, and that is, we've seen Arizona, so how do we compare with the other states in the Southwest, New Mexico, Southern California, Colorado, versus the rest of the country?
As far as trends?
As far as trends, as far as climate change, I think we saw a huge evolution of climate change when this heat dome went up to Canada.
Yeah, so
this year.
Right. Yeah, so temperature trends, the Southwest has had some of the strongest temperature trends of any place in the country. You have to kind of go up to Alaska to see even stronger temperature trends. So we really are kind of leading the charge. Part of it is that we have also, at the same time that this warming has really popped up, is that we've fallen into a drought cycle. So that drought cycle has really helped those temperatures really race out ahead of us. So it'll be interesting to see. We do, as best we understand, we will enter another wet cycle. We don't know if that'll be in 5 years or 30 years, but it'll be under a warmer climate, and that should kind of help bring temperatures down a little bit, but it'll still be as we're getting warmer at the same time. So right now, we really are kind of racing out ahead of everybody as far as temperature trends.
So what you're then saying is that you're seeing at least the western half of the US going to climate change, getting warmer. Definitely.
Yes, that's right. That's right.
And growing. And perhaps the eastern half of the US staying temperature-wise the same, but getting more water.
Yeah.
So
that's
here's a comical question. If I were going to want to move now, where would I move to? What state?
I get that question all the time. I should go into real estate. You know, you know, Arizona's got, I mean, we've got some challenges ahead of it. I think everybody's got some challenges. I'm from the upper Midwest. I'm from Michigan. And it's interesting to kind of think about some of the regional challenges and opportunities, right? So the upper Midwest has got plenty of water, but it's also getting warmer, and they're getting more rain and more storms. They're getting more insect-borne diseases because, you know, it's wetter and warmer during the summer. So they'll having more heat waves, and they don't have quite the infrastructure to deal with it. And then you come down to the Southwest, we have all of this infrastructure to deal with extreme heat for the most part, unless you're, you know, kind of a marginalized population or you're homeless, which is not good, and we need to fix that. But we have this water situation at the same time. So, you know, our challenge, we've got all this infrastructure around dealing with heat, but we don't have the water on top of it. You know, if we could get that dialed in, we've got some flexibility and sustainability down here if we could deal with that. California, as you see, has got all of these new challenges that they thought they had kind of wrapped up. The fire situation in the wildland urban interface is a huge challenge. And some of these forests that hadn't burned in a long time are burning now. The Southeast has got even more humidity now, and tropical storm and sea level rise. I don't know, maybe central Canada, maybe the plains of Canada is going to be the new the place to sort of locate. It's beautiful.
Yes, it is.
Another question that came in the chat was, is this same type of modeling that you showed done with different countries such as India and China, where greenhouse gases are more prevalent?
Yes, that's a great question. So like these models, this is an average of about 30 different modeling groups. Might have that wrong. Maybe 15 on this particular one, but it's an international modeling effort, and it's everybody. It's European countries, several models from the US, China, India, Australia, Russia has a model in here as well. And so the idea is that these models do different things well, and some work better in some regions than other regions, and some have better, they're tuned up to do different things. And so the idea is that if you average them all together, you get something that is hopefully closer to the truth than any one model. And this is advancing too, is to try to then pick out the right model from the right country for the right region based on how it's performed in the past. But we still, as we've gone forward, still see that averaging them all together makes the most sense when we're doing these planning exercises.
Awesome. Well, thank you so much, Mike, for coming and doing this presentation with us tonight. That was super interesting.
Okay, great.
So I had a great time. Are there any other questions before I show some Highlands Center stuff? Is there anything you want to plug?
No, just thanks for having me present virtually. It's great to be able to do this from Tucson, but I'll enjoy getting back up to Prescott and seeing y'all sometime.
Yeah, that'd be awesome. Well, great.
All right.
I'll
give you the screen back too.
Thank you. I always forget how to take it back. Awesome. So as I said, we have a really exciting fall coming up. This is our website, highlandscenter.org. Of course, you can always call us or visit us, but our website has all the information. I will bring up, we have plant sale going on right now. If you want to plant some native plants, they are, most of them are, what's the word? They don't need a lot of water. They're very low water plants. So if you're interested, you can click on under events, the Grow Native Plant Sale. I also want to plug Hiking Spree if you want to get out and hike. We have the Hiking Spree starting September 4th. If you attempt 8 out of the 10 hikes and you turn in a form saying that you did so, you are entered into a raffle to win a $300 gift certificate from the Hike Shack. So it's also just a great way to get outside and see Arizona, especially the central Arizona Highlands. And if you're ever interested in adult programs like this one, you can find them under education programs, adult programs. We're not going to have a Zoom for September, but hopefully in October. So look for that here on our adult programs. And we have our book club, which is free. We have a community nature study series. So September 14th, you should sign up for our newsletter. That way you get emails about everything we're doing. But we have a couple different classes, one on the Arctic, one on the physics behind different feather colors. And this is presented by our recent Embry-Riddle graduate student. He's an intern with us. And Precious Waters by Krista Sadler. We also have a happy hour coming up with mushrooms on October 7th. So yeah, it's gonna be a lot of fun. And I hope to see you all there. And if you ever need anything, you can reach out to me. I'm the person who emailed you. I'm Erin Nixon, and I'm the Adult and Community Education Coordinator at the Highlands Center. So everything I just plugged is something that I worked on. So I should be able to answer any questions that you have. Thank you all for coming and supporting us, and I hope to see you again soon.